Dear students, today we shall take up some problems in electrostatic potential. Here is the first problem. Two tiny spheres carrying charges 1.5 microcoulomb and plus 2.5 microcoulomb are located 30 centimeter apart. Find the electric potential, number 1, at the point midway on the line joining the two charges. Number 2, at a point 10 centimeter from 2.5 microcoulomb charge on the line passing through the charges. See, you can read the problem here. First problem. Just you pause the video and you read the problem once and then you try to solve it. So, according to the problem given here, there are two tiny spheres having charge. You know that a charged sphere acts like a point charge. Here this is one tiny sphere which acts like a point charge of a plus 1.5 microcoulomb. Here there is another tiny sphere which acts like a point charge of plus 2.5 microcoulomb. It is given that these two are separated by 30 centimeter. That means 0.3 meter. So in the first part of the problem, you are asked to find electric potential at the midpoint on the line joining the two charges. Say this is A, this is B. So this is the midpoint of the line joining the two charges. So at this point, you are asked to find the potential. So at the midpoint on the line joining the two charges, you are asked to find electric potential, that is C. You know that electric potential is a scalar quantity. So, potential at this point, according to principle of superposition, it is the sum of potentials due to individual charges. That means potential at C due to the charge at A plus potential at C due to the charge at B. So, this is 1 by 4 pi epsilon naught charge at A QA divided by this distance CA, 1 by 4 pi epsilon naught QB divided by CB. You know this formula, electric potential at a point due to a point charge. So here you can take this 1 by 4 pi epsilon naught, which is 9 into 10 to the power of 9 common. In these both charges are microcoulomb charges, so 10 to the power of minus 6 is common. And this distance is also equal. A to C and C to B, it is equal, that is 0.15. So sum of these two charges means it is 1.5 plus 2.5. So this is 9 into 10 to the power of 3. When you add these two things, you get 4 divided by 0.15. So if you do this calculation, roughly you will get 2.4 into 10 to the power of 5 volt. So this is the first part of the problem. In the second part of the problem, at a point 10 centimeter from 2.5 microcoulomb charge on the line passing through the charges, you are asked to find the potential. That means from this 2.5 microcoulomb charge at this distance 10 centimeter, that means 0.1 meter, you are asked to find the potential. So you carry the derivation in the same way. Electric potential at 10 centimeter from 2.5 microcoulomb charge, that is Vd. This 1 by 4 pi epsilon naught common, QA divided by AD plus QB divided by BD. Sum of potentials into individual charges. So it is 9 into 10 to the power of 9. Both are microcoulomb charges, so 10 to the power of minus 6 is common. And this is 1.5 and this distance AD. So 0.3 plus 1 plus 0.1, so it is 0.4. QB 2.5 divided by BD 0.1. You simplify this one, you will get nearly 2.59 or 2.6 into 10 to the power of 5. So in the theory, you studied about electric potential at a point due to multiple charges. So from the principle of superposition, the potential at any point is equal to sum of potentials due to individual charges. Based on that principle, this problem can be solved. So this is the first one. Next, the second problem. You look at here. You pause the video for a few seconds and you read that problem. The second problem, it goes like this. There are two charges separated by 15 centimeter apart. So the first charge is 3 into 10 to the power of minus 8 coulomb, and the second one is 2 into 10 to the power of minus 8 coulomb. These two are separated by 15 centimeter. That means 0.15 meter. Now you are asked to find at what point on the line joining the two charges electric potential is 0. So here this is the line joining the two charges. You are asked to find the point where the potential is 0. See, when both charges are positive, if both charges are positive or if both charges are negative, nowhere the potential can become 0. So potential can become 0 if one charge is positive, another charge is negative, like this. Because if both are similar charges, then just potential adds up. You learned that potential due to a positive charge is positive, potential due to a negative charge is negative. Here, if potential is to be 0, one charge must be positive, another charge should be negative. When unlike charges are there like this, there will be 2 points where the potential can become 0. One point lies in between the line joining the two charges, another point lies outside the line joining the two charges. So we shall find the first case. This is A, this is B, this is O. Let this distance be X. The remaining distance will become 0.15 minus X. Let X be distance from 3 in 10 to the power of minus 8 coulomb, where electric potential is 0. That means potential at O due to the charge at A plus potential at O due to the charge at B, this is equal to 0. That means this 1 by 4 pi epsilon naught charge at A divided by OA plus charge at B divided by OB, this is equal to 0. Now this is 9 into 10 to the power of 9, this 10 to the power of minus 8, it is common, so this is 3 divided by x minus 2 divided by 0.15 minus x, this is equal to 0. So here when you take this term this side, it becomes 0, therefore this 3 divided by x is equal to 2 divided by 0.15 minus x. When I cross multiply, .45 minus 3x is equal to 2x. So 5x is equal to 0.45, x is equal to 0.09, therefore x is equal to 9 centimeter. So at a distance 9 centimeter from 3 in 10 to the power of minus 8 coulomb charge, the electric potential can become 0. So due to the positive charge, whatever potential is there, due to the negative charge, equal amount of potential is there here, therefore the net potential will become 0. So this is the first part of the problem. So when two unlike charges are there, if you are asked to find the point where the potential can be 0, there will be two positions where the potential can be 0. One is in between the line joining the two charges, this is the one. There must be one more point either this side or this side. If I consider some point here, this distance being smaller and this charge being larger, potential due to this larger charge will be always more than the potential due to this smaller charge. Therefore, nowhere towards the larger charge the potential can become 0. It's not possible. So obviously, there must be lying some point here. So this charge is smaller, distance is smaller, because V, it is proportional to Q divided by R. So if V is to be 0, that means V must be 0, means this Q, V must be constant. So Q should be proportional to R. That means so for smaller charge there will be a smaller distance, and for larger charge there must be a larger distance. At such a point the potential can be constant. That means here it is 0. Because this V is proportional to Q by R. V is 0 means it is constant. That means Q is proportional to R. So due to two charges, if the potential is to be a constant, then Q must be proportional to R. Smaller the charge, smaller must be the distance. Larger the charge, larger must be the distance. At such a point only the potential can become constant. In this case it is 0. So here we shall take this distance as x now. So this point is C. We take this distance as x. Let x be distance from minus 2 into 10 to the power of minus 8 coulomb, where electric potential can be 0. So therefore this VCA plus VCB should become equal to 0. That means 1 by 4 pi epsilon naught QA divided by AC plus QB divided by BC, this should be 0. So again, if you do similar type of calculation here, 9 into 10 to the power of 9 into 10 to the power of minus 8, 3 divided by 0.15 plus x minus 2 divided by x. This is equal to 0. So this term, when it goes this side, it becomes 0. Therefore, this 3 divided by 0.15 plus x is equal to 2 divided by x. When I cross multiply 3x, when I cross multiply 3x is equal to 0.3 plus 2x. So here 3x is equal to 0.3 plus 2x. So therefore x is equal to 0.3 meter. That means at 0.3 meter from minus 2 into 10 to the power of minus 8 coulomb, the electric potential can become 0. Or otherwise, if I take the distance from here to here, so this is 0.15, this is 0.3, so this distance will become 0.45. So at 0.45 meter from 3 into 10 to the power of minus 8 coulomb, the potential can become 0. So from this charge at this distance, potential can become 0. See, whenever you are asked to find the point where the potential can become 0, you have to identify the various options where the potential can be 0, whether in between the line joining the two charges and outside the line joining the two charges towards the larger charge or towards the smaller charge. So in this case, because of this relation, here at this particular point, at this distance, the potential can become 0. Now I shall go to the next problem. You look at this third problem now. Third one, just you pause the video and you read that problem once. In this third problem, it is given that a charge of 20 microcoulomb produces an electric field. Here at O in air, there is a charge of 20 microcoulomb. It is producing some electric field. 2 points are 5 centimeter and 10 centimeter from this charge along a straight line on the same side. So here this is the same side of the charge. There are 2 points here. One point is 5 centimeter like this. Another point is 10 centimeter like this. So this point is P and this point is Q. Now the question is, find the potentials at these points. Also find the work done to move an electron between these points. So you are asked to find the potentials here. You are asked to find the work done to move an electron between these points from one point to another point. So these type of simple problems will only be asked in the board examination. Only thing is, you should know which formula to be used to get the solution. So this being a point charge, electric potential at a point will be a point charge. So electric potential at P. So electric potential at P due to the charge at O. This is 1 by 4 pi epsilon naught QO divided by this distance OP. So this is 9 into 10 to the power of 9, 20 into 10 to the power of minus 6 divided by 0.05. So this is 9 into 10 to the power of 3, 20 divided by 5 into 10 to the power of minus 2, so it cancels 4 times. So it is 36 into 10 to the power of 5. 36 into 10 to the power of 5 volt. Similarly, electric potential at Q. Electric potential at Q. So OQ, the same formula. So if you do the substitution, 9 into 10 to the power of 9, 20 into 10 to the power of minus 6 divided by 0.1. So if you do this calculation, you will get 18 into 10 to the power of 5 volt. It is very simple. Charge is same. The distance being doubled, potential becomes half. So it becomes 18 10 to the power of 5. Now the question is, work done in moving an electron from one point to another point. So how to find this work done? As I told you while explaining the concept, work done is potential difference into charge. So work done in moving electron from one point to another. W is equal to potential difference into charge. So this is what you learned. So potential difference means here VQ minus VP. VOQ, sorry, where the field is stronger, VP, where the potential is stronger, VPO, QO into E. So this is 36 minus 18 10 to the power of 5 into 1.6 into 10 to the power of minus 19. If you do this calculation, you will get 2.58 10 to the power of minus 13 joule. So this becomes the negative work done. So this is the work done in moving electron from one point to another. Now you look at the next problem. Fourth one. You read that fourth problem. Here, in this fourth problem, it is given that there are point charges of plus 4 nanocoulomb, plus 6 nanocoulomb, minus 8 nanocoulomb, plus 10 nanocoulomb are placed at the corners of a square of side 0.02 root 2 meter. Find the potential energy of plus 1 microcoulomb charge. Find the potential energy of a plus 1 microcoulomb charge placed at the center of the square. So here, this is the center of the square. If I consider a plus 1 microcoulomb charge here at the center, plus 1 microcoulomb charge at the center, You are asked to find the potential. See, this problem can be solved in two different ways. One way of doing this is finding potential energy between all pairs of charges and adding them. So potential energy of a pair of charges is given by U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. That gives potential energy for a pair of charges. So here 5 charges are there. 4 plus 1, 5 charges are there. That means how many terms will be there? N into n minus 1 divided by 2. So 5 into 4 divided by 2. So 10 terms will get. First, these two, these two, these two, these two. You will get 4 terms. These two, these two, these two, and these two. You will get another 4 terms. These two, and then these two. Another 2 terms. You will get totally 10 terms. So you find the potential energy of 10 pairs of charges, you will get total potential energy of the system. This is one way of doing this problem. Other than this, rather a simple way is, you know that potential energy or work done is equal to potential difference or electric potential into charge. So here you know this relation. Potential energy or work done, this is equal to electric potential or potential difference into charge. So first you find the electric potential at O due to all these 4 charges. You will get net potential, and you multiply the charge at O. That gives the potential energy of the charge at O. This is the rather simplest way of solving this problem. This is the easiest way of solving this problem. So instead of taking 10 pairs of charges and adding potential energy, sometimes if you forget to take any one pair, you will get wrong answer. So instead of that, this is the simplest way. So first you find the electric potential at O due to all the charges. Electric potential at O due to the charges VO. So at this point, due to these 4 charges, the potential is given by potential at O due to the charge at A, potential at O due to the charge at B, potential at O due to the charge at C, and potential at O due to the charge at D. So if I write the formula, this 1 by 4 pi epsilon naught is common, and say this is A, B, how these charges are given? 4, 6, minus 8, 10. 4, 6, minus 8, 10. That means this is A, B, C, D. Like this. So it is QA, charge at A divided by the distance OA. Charge at plus charge at B divided by the distance OB, plus charge at C divided by distance OC. Charge at D divided by distance OD. So here, this 9 into 10 to the power of 9. All are nanocoulomb charges, so 10 to the power of minus 9 is common. And OA, OB, OC, OD, they are equal. This distance is equal to this one and this one and this one, all are equal. So half the length of the diagonal means 1 by root 2 times the side. That is 0.02. Length of the diagonal means root 2 times the side. Half the length of the diagonal means 1 by root 2 times the side. So this term divided by root 2. It is 0.02. Otherwise write one more step. There is nothing wrong in it. 0.02 root 2 divided by root 2. And you are left with the charges here now. So this is plus 4, this is plus 6, this is minus 8, and this is plus 10. So this potential at O, so this is 9, this 10 power plus 9 minus 9 cancels, this root 2 cancels, so 9 into 10 plus 10 20, 20 minus 8, 12 divided by 2 into 10 to the power of minus 2. So 20 minus 8 is 12. So 9 into 12 divided by 2 into 10 to the power of minus 2. So it cancels 6 times. So 54 in 10 to the power of 2. So it is 5400 volt. This is the potential at O. Therefore, potential energy of plus 1 microcoulomb charge kept at O is U is equal to Q into V. So 1 into 10 to the power of minus 6 into 5400. So this is 5.4 into 10 to the power of minus 3 joule. This is the answer. So 5.4 into 10 to the power of minus 3 joule. So this is the simplest way of solving this problem. Now we shall take one more. Fifth one. This one. I hope you can see the fifth problem. You pause the video for a few seconds and you read it. And now you should solve the problem. In the fifth problem, it is given that ABCD is a square of side 0.2 meter. Charges of minus 2 nanocoulomb, plus 4 nanocoulomb, 12 nanocoulomb are placed at the corners A, B and C respectively. Calculate the work required to transfer a charge of 4 nanocoulomb from D to the center of the square. These type of problems were asked in the annual examination many times. So here 3 charges are kept at the 3 corners of a square. You are asked to find the work done in moving a 4 nanocoulomb charge from D to O. From here to here, if I have to move a 4 nanocoulomb charge, how much work is done? As I already told you, whenever you need to find work done in moving a charge between 2 points, you have to use the same formula. Work done is equal to potential difference between those 2 points into charge. So first you have to find the potential difference here. That means first you find the potential at O due to these 3 charges. You find the potential at D due to the same 3 charges. You find the potential difference. That potential difference into charge to be moved, that will give you the work done in moving the charge. So first you find electric potential at O due to the charges. So electric potential at O due to the charges at A, B, C, it is given by this equation. Electric potential at O due to the charges at A, B and C. You write the formula like this. Now you do substitution. So 9 into 10 to the power of 9, this is 1 by 4 pi epsilon naught. All these are nanocoulomb charges, so 10 to the power of minus 9 is common. And this distance is same. That is half the length of the diagonal is 1 by root 2 times the side. So 0.2 divided by root 2, and the charges are minus 2 plus 4 plus 12. So this is 9 into root 2 into 14 divided by 0.2. So you find this value. You find this value. You will get V0 volt. Similarly, electric potential at D due to the charges. Due to these three charges, you find the potential at D. That is Vd. How to find the potential at D? By using the formula for electric potential at a point due to a point charge. So 1 by 4 pi epsilon naught is common. Else you write one more step here. Vd is equal to Vda plus Vdb plus Vdc Qa divided by Vd, this distance, Qb divided by Bd, Qc divided by Cb. Now you simplify this. This is 1 by 4 pi epsilon naught. All are nanocoulomb charges, so you can take 10 to the power of minus 9 common. The charge is minus 2. What is this distance? 0.2. And the charge at B is 4 nanocoulomb. 4. What is the distance of the diagonal? I mean length of the diagonal. Root 2 times the side. So 0.2 root 2 or root 2 into 0.2. Then what is the next charge? 12 nanocoulomb. 12 divided by, what is the distance? DC? 0.2. So you simplify this one. So it is 9. It becomes a minus 10. So this is a 10 by root 2. By root 2. Plus 60. So this is 9 into 50 plus 20 by root 2. So this is Vd. You find this value. Therefore, potential difference between the points O and D is V is equal to V0 minus Vd. So actually, these distances being smaller, the potential at O is stronger than potential at D. Therefore, the potential difference is V0 minus Vd. Therefore, so you find this value. You calculate this V0 here. You calculate this Vd here, and the potential difference means V naught minus Vd. Therefore, work done in moving 4 microcoulomb from D to O, lower potential to higher potential. Here potential is lower, here potential is higher. So when charge is got to be moved from lower potential, positive charge is got to be moved from lower potential to higher potential, positive work is to be done. So therefore, this W is equal to Q into V. You know this Q plus 4 microcoulomb, you know this V. So you do this substitution calculation. You will get the amount of work done in moving the charge from D to O. So you just remember, whenever you ask to find the work done, it must be either electric potential into charge or potential difference into charge. When two specific points are given, then obviously it becomes potential difference. So you take this value of Q and V here in this formula and do the calculation for W. You check whether you get (1.26) into 10 to the power of minus 6 joule. You are supposed to get this much. You check whether you get this answer or not. So tomorrow or in the next class we shall take few more problems in this electric potential.